We are entering into the next lecture discussing about the rigid rotor problem. Let's quickly revise it so that we recollect what we were thinking about. We were discussing about two masses m1 and m2 that are separated by a distance r. We set up the Hamiltonian, which is minus h cross square by 2m del square in the Cartesian space, which gets converted to the short minus h cross square by 2mr square 1 over sine theta dou by dou theta sine theta dou by dou theta plus 1 over sine square theta dou square by dou phi square, where r is a constant. This is what we saw in the previous classes. Then what we ended up doing was to solve the eigenvalue equation h psi equal to E psi, the Schrodinger's equation. Once as we start solving it, we realize that the way to go forward is to do separation of variables, where you come up with psi as capital theta times capital psi, and then while you go forward you realize that you have an equation that comes up as a sum of only theta only terms, phi only terms, that equates to 0. We set the phi part to minus m square, theta part to plus m square. While we do it, what ends up happening is that we find the phi part given by the solution of the particle in a ring, where m can take the value of 0, plus minus 1, plus minus 2, and so on, with the energy given by m square h cross square by 2i. Similarly, the theta part, we end up solving by theta by capital theta dou by dou theta sine theta dou by dou theta of capital theta plus beta sine square theta small theta is equal to m square. When we ended up solving this, we had to assume, or rather we solved it using the power series, where the solution for beta comes as L into L plus 1. And as we go forward, we make further assumptions where we say set x equal to cos theta and capital theta to the Legendre polynomials p of x. I would like to reiterate the fact that one has to be careful with this, because this x is not the x, y, and z we started with. You have to assume it's a different variable. This was a point that I didn't touch upon last time. Okay, so now you have something like this. What we understood was that for value of m equal to 0, these are nothing but the Legendre polynomials, where p of 0 of x equal to 1, p of 1 of x equal to x, p of 2 of x is 1 over 2 3x square minus 1, p of 3 is something like 1 over 2 5x cube minus 3x, and so on. Then we also said there are associated Legendre polynomials that can be deduced from this, where we try to say for values not equal to m not equal to 0, you tend to say this will be given by 1 minus x square mod m divided by 2 times dm, the mth differential with respect to the new variable x, of pl of mod m of x. Right? So this is how we would be able to determine what are the associated Legendre polynomials when a value of m greater than not equal to 0 ends up coming. So this is what we learnt in the last class. So while we solved it, the things that we were finally coming up with, therefore the solution of the spherical harmonics YLM, meaning that the two quantum numbers L and M as a function of theta and phi, will be given by 2L plus 1 by 4 pi times L minus mod m the whole factorial divided by L plus mod m the whole factorial, the whole power of half. This is the normalization constant that comes up. Then P mod m as a function of cos theta, we convert x back to in theta terms, e power I m phi. So this is the theta part, this is the phi part, and this is the normalization constant that comes up. Why don't we see whether we are able to deduce some spherical harmonics from this? So let's say what is y 0 of 0? L equal to 0 is an allowed value. So what is y 0 of 0? That is going to be equal to 2 times 0 plus 1 by 4 pi times L, which is 0 minus mod 0 divided by 0 plus mod 0, the whole factorial in both the cases, the whole power half. And we know for a fact that P 0 of 0 is nothing but 1, right? And e power I times 0 times phi, because m is also 0. So this will result in 1 over square root of 4 pi times 1. So that is your first spherical harmonic solution. Then let's take a look at what is y1 of 0. That is going to be equal to 2 times 1, that is 2, plus 1 divided by 4 pi times L, which is 1 minus 0 the factorial, 1 plus 0 factorial, the whole power half. I would like to remind the students that 0 factorial is indeed equal to 1. So we have P1 of 0 of cos theta times e power I times 0 times phi, because m value is equal to 0. So now what ends up happening? This value was nothing but x, so this remains cos theta. And you see that this is 1 factorial by 1 factorial. This is 3 by 4 pi, so therefore it's going to be square root of 3 by 4 pi times cos theta times 1. So this is the y1 0. So let's also try to determine what is y11. y11 will be equal to 2l plus 1, that is 3, divided by 4 pi times l minus 0 factorial, so 1 minus 1 factor, 1 minus 1, which is 0 factorial, divided by 1 plus 1, that is 2 factorial, the whole power half, times p 1 of mod 1. Remember, we can write this as plus minus 1, right? So that is going to be equal to, if you might remember from the last class, plus minus 1 phi. You might remember this was equal to sine theta. So this becomes equal to square root of 3 by 8 pi times sine theta times e power plus minus I phi. So similarly, you would be able to determine what is y02, what is y02 plus minus 1, and y2 plus minus 2. Why are we spending so much time understanding this? Is because if you are able to deduce this, as we go forward, you will be able to understand how orbitals come up. Orbitals will nothing but be a linear combination of these wave functions that ends up coming. Good. So far so good. Let's come back to the whole thing where we realized the Hamiltonian, when operated on YLM, is going to give you h cross square by 2i L into L plus 1 YLM back. I would like to reiterate the fact that you get back the same function with a constant. Therefore, YLM is an eigen function of the Hamiltonian operator. And as you guys might remember, we said that the Hamiltonian is given by L square by 2i. So therefore, what does this make it? When you operate L square on YLM, you are going to get h cross square L into L plus 1 YLM. So this is not surprising, because the Hamiltonian and the total angular momentum commute with each other, means that they have a common set of eigenfunctions, which is YLM. Of course, their eigenvalues are different. We only say their eigenfunctions. They both share a set of eigenfunctions. Okay, and remember the solutions of all this, since these are all Hermitian operators, would end up being orthogonal to each other. With the normalization that we have done, they also are orthonormal. So Y, Lm are orthonormal basis set in the basis that is generated by the Hamiltonian and the angular momentum operator. Let's revise a little bit of the angular momentum operator. We said that L equal to R cross P, where the R vector we said is xi cap plus yj cap plus zk cap, and then the P is given by pxi cap, py j cap plus pz k cap, right? So these were the operators that we had in hand, and we were able to deduce it where the component Lx will be given by y times pz minus z times py. Ly will be given by z times px minus x times pz. Lz will be given by x times pz minus z times px. But remember, we have moved away from the x, y, z system to the r, theta, phi coordinate system, right? So once we have moved into a different coordinate system, we should also convert Lx, Ly and Lz in terms of r, theta, phi. Instead of going to the entire rigor, I'm sure you guys will be able to do the basic algebra. You can also find the solution of converting Lx, Ly, Lz from Cartesian to spherical polar coordinates in the textbook written by Levine. So rather than going into the rigor of doing the mathematics to convert it, I'm going to give you the solutions right away, where Lx will be given by minus IH cross minus sine theta dou by dou theta minus cot theta cos phi dou by dou phi. Ly, of course, whenever we mean operator, we need to put a cap on their head. So ensure that you put a cap on each one of them. Right, so minus IH cross cos theta dou by dou theta minus cot theta sine phi dou by dou phi. Lz will be given by minus IH cross dou by dou phi. Of course, if you have the patience, you can calculate what L square will be given as. That will nothing but be Lx square plus Ly square plus Lz square. I'll leave it once again up to you guys to figure out how to write L square in spherical polar coordinates. But not wasting further much time, I'm sure you guys remember L square times Lz, we had remembered to give 0. Similarly, L square Lx is 0 and L square Ly independently, each one of them independently commutes with the total angular momentum. However, each of the component with respect to itself do not. So basically we came up with this circular equation where Lj will be given by epsilon ijk, where epsilon ijk is plus 1 when ijk is cyclic and minus 1 when it's acyclic, times I h cross Lk. We had derived this earlier using the operator algebra, but now what I'm trying to say is that you can repeat the entire process by using this Lx, Ly and determine that whether you get Lz back. I will not be doing this because it's simple arithmetic, and if you do it calmly, you will be able to get this. Okay, now having understood this, why did we spend so much time understanding the angular momentum operator? We just learned that the Hamiltonian and the angular momentum operator commute with each other. So therefore, if you are able to find anything with respect to the angular momentum, you can extrapolate it back to the Hamiltonian, right? So once we have understood this, and let me write the other operators, other commutators that would end up coming, right? Once we have written all this, the next step would be in understanding, okay, how can we exploit them? So let me also write a few more things because I might keep exchanging myself to different notations. YLM as a function of theta and phi can also be written in the Ket notation, the Dirac Ket notation. So if I say L comma M, this indicates the quantum number L and M for the spherical harmonics. So when we say L square on YLM, that should give you H cross square L into L plus 1 back the YLM. So this can also be written as L square L comma M will be given by h cross square L into L plus 1 L comma M. On the other hand, Lz on L comma M in the Ket notation will give you h cross times M L comma M. We realize that we start with the function, get the function back with a constant. So that these are the nothing but rewriting the eigenvalue equation in different forms. Okay, so now having said that, we will continue further to see a few more identities with respect to the angular momentum operator. Let's try to calculate what is L square minus Lz square YLM. This will be equal to L square YLM minus Lz square YLM. And this is nothing but h cross square L into L plus 1 minus h cross square M square the whole bracket YLM. Luckily L square and Lz commute, so they will give the same thing back. So what you're able to see here, this is going to be equal to h cross square L into L plus 1 minus M square YLM. But remember, L square minus Lz square is also Lx square plus Ly square. How did I write it? L square is nothing but Lx square plus Ly square plus Lz square, and if you subtract Lz square from it, you will end up getting something like this. Okay, so this is an important step for everybody to understand. You see that the sum of squares, in this case neither of them are complex numbers, so sum of squares, even if they are complex numbers, you're going to get a I star I, which will make them a real number, and they are multiplication with each other, so therefore this value will always be greater or equal to 0. So that implies the right hand side is greater than 0. So let's rewrite it. H cross square L into L plus 1 minus M square YLM is greater or equal to 0. Of course, the function YLM is not equal to 0. We have seen it for very different functions, but even if that's equal to 0, it makes it trivial. We know for a fact that the Planck's constant is also not equal to 0. So that could imply, so this is what you're trying to look at. Basically, none of them are values that could go less than 0, YLM and H cross square. So therefore, this is the value that we have to look into more closely. L into L plus 1 is therefore greater or equal to M square, and since L cannot take negative values and M can, this limits the fact when you take a square root that mod M can at the maximum have a value of L, and M is restricted by the L quantum number. This has been known to you from early days in your school, where the M quantum number is restricted by L, and we had also used it last time. So therefore, now what ends up happening, M will be given by 0, plus minus 1, plus minus 2 until plus minus L. Although we used it in the last class, this simple deduction helps you understand how things get set. So therefore, for a given value of L, you're going to have 2L plus 1 number of states that are present. So this is how the degeneracy ends up coming for the rigid rotor problem. Okay, fantastic. So now that we have understood this, let's try to get a physical picture. Let's take a value of L equal to 1. If L is equal to 1, M can take the values 0 and plus minus 1. It cannot take the values plus minus 2 because it is limited. So L square on 1 comma 0 or to L square 1 comma 1 to L square 1 comma minus 1, which will be equal to h cross square L into L plus 1. So this implies L square for any of these quantum numbers is going to be h cross square times 2. This implies mod of L will be equal to square root of 2 times h cross. So similarly, if you apply Lz, for the sake of simplicity, let's take 1 comma 0, you're going to get 0. Lz of 1 comma minus 1, you're going to get minus 1. Lz comma 1 comma plus 1 will give you plus 1. So now you have something of this sort where the z projection can be, okay, of course I missed h cross, plus 1 h cross and minus 1 h cross, while the magnitude of this vector is square root of 2 h cross, and you realize square root of 2 is greater than 1. So the projection that comes up as h cross by 2, 0, and of course I need to extend it to minus z axis, has a projection here of minus h cross by 2. And then when you have this vector, the magnitude of this vector is square root 2 times h. So by basic trigonometry, one should be able to understand what is the angle theta here. So what will be the angle theta? You have something like cos theta, sorry, this won't be h cross by 2, it will just be h cross. So you're going to get cos theta is going to be equal to 1 divided by square root of 2, where theta is pi by 4 or 45 degrees, right? So this means that LZ and L are not collinear with each other, and of course there are other vectors in this as well, each of which has the same magnitude of the length of the vector, but the projection on the z-axis is different. So now, having said this, we are able to determine theta out of the YLM. We say YLM as a function of theta comma phi. We are able to reliably determine what is theta. Now the question is, what is phi? What is phi question will be answered in a moment, but what we are able to realize here, the vector is not collinear with the xz, not with the z-axis. Okay, now having found this, let's move on and introduce a few more angular momentum operators. And these operators are actually familiar for you guys, largely because we introduced them in the model called the simple harmonic oscillators. Yes, you have guessed it right. We are talking about the raising and lowering operators. So you can have L plus minus, which will be equal to Lx plus or minus ILY. If it's L plus, it's Lx plus ILY. If it's L minus, it's Lx minus ILY. Okay, so these operators we had seen before. We will try to use these operators again. So let's take a look at some commutation relationships. What is L plus minus comma Lz? So this is going to be equal to Lx comma Lz plus I Ly comma Lz. Lx comma Lz, since this is acyclic, you have a minus 1 h cross Ly plus I times Yz is cyclic, so you have plus I h cross Lx. So this will be minus I h cross Ly minus I square h cross Lx. I square will be plus I square h cross Lx. So I square will be minus 1. This will be equal to minus h cross Lx plus I Ly. So you get something like this. Of course, on the way I missed plus minus here, plus minus here, plus minus here, plus minus here. So therefore this is going to be equal to, did I do that right? No. So once this is switching, this will be minus plus. So basically what you will end up getting is that it's minus h cross Lx minus plus Ly. So therefore this is going to be equal to now this is fine. You still take a minus sign out. When you take a minus sign out, what ends up happening? That will be equal to L plus minus. Let me quickly make sure my solution is correct. Yes. So this is important. L plus minus comma Lz commutator is equal to, this will be extremely crucial when we determine how the ladder up, ladder down operators work. Similar to the harmonic oscillator, it's going to change the quantum number. We'll take a look at what quantum number does it change. So once again, that will be the next question. What does L plus minus do to YLM? So to answer this question, we will take a little different route, where we are able to realize that we just solved L plus minus on Lz is equal to minus h cross L plus minus. Generally when you have a commutator, you need to operate it on a function Lz YLM is equal to minus h cross L plus minus YLM. So when you get this, let's write the commutator in its full glory. Lz YLM minus Lz L plus minus YLM equal to minus h cross L plus minus YLM. So therefore you have to operate this first. We just need to know what this is, so we won't be processing this yet, but we are able to see L plus minus and YLM will be M H cross L plus minus YLM minus LZ L plus minus YLM equal to minus H cross L plus minus YLM. So when you have this, you see that on either side you have L plus minus YLM. So if you take this onto the left side, that onto the right side, or rather we do the opposite and multiply by minus 1, LZ plus minus YLM will be equal to MH cross L plus minus YLM plus H cross L plus minus YLM. So therefore Lz on L plus minus YLM will be equal to H cross is common, M, oh yeah, I missed a plus minus here. So if you realize there's also another plus minus that will end up coming in this relation. This will be a minus plus, minus plus, minus plus, minus plus, minus plus. When you take minus plus on the other side, it will become plus minus. So you will get something like M plus minus 1 L plus minus YLM. So this is an important conclusion to make. You realize that if Lz operates on L plus minus YLM, it gives back L plus minus YLM. That means that L plus minus of YLM is also an eigenfunction of the Lz operator, similar to YLM itself. But on the other hand, instead of giving MH cross, it ends up giving a value that is different, meaning that if you're operating with plus, it gives an M plus 1. If you're operating with a minus, it gives you minus 1. So this clearly indicates L plus will increment M quantum number by 1 unit. Similarly, L minus will decrement M quantum number by 1 unit. So this is the same thing that we have seen for the harmonic oscillator as well. We will then see in the following lecture how other features of the angular momentum operators works out. Thank you very much for your attention.